Good evening, everybody. Welcome to a special edition of Chem 170 with your host, me, Dr. White. And I'll be doing the review for test number 4. Let me remind you, this coming Monday, I will be giving test number 4. I've already shown you and sent out an email of the point breakdown in test number 4. But if you look at that, there's a lot of things you should know. What do I call that? I have a mental break right now. But anyways, hold on. I really do have a mental block. Huh. General knowledge. I don't know. I haven't why I had a mental block. But if you look, there's a lot of general knowledge points, like 57, which is not, what's my hair there? It's gone. But anyways, that's because if I ask you, is my right hand chiral or achiral? Well, it's not nomenclature. It's not reactions. It must be general knowledge. So that's why it is. So on Monday, we will have test number 4. Also, on next Thursday, a week from tonight, will be the final exam. Sometime tomorrow, I will post information about the final exam. But I do want to tell you, the best way to study for the final exam is use each of your problem sets. What am I saying? Each of your tests, 1, 2, 3, and 4, as practice problems. And that will help you do good on the final. I can't do the letter F. That. But anyways, the final exam. Use your tests as practice problems. Now, I'll also put out an email, an announcement that which videos you should watch where I do the review for the whole final. And with that, I better get going with test number 4 review. Oh, one other thing. Bear with me because this is very important. If you go to D2L, click on content. This is very important. And you're in the lectures. Now, I might have mentioned this and I might have forgotten. If you scroll all the way to bottom, it only goes to chapter 11 and 13 of means. What about the reviews? See here where it says load more at the very bottom of the lecture section. This is a bad thing about D2L, because why don't they have it on one screen? You can scroll down, because this is an old software and they don't know how to do that. But click on load more again in the lecture section of Blackboard, wrong school, D2L, scroll to the bottom, click on load more, and now you see the more stuff that are the chapters we just covered, and also all the reviews. All right. Also, let me remind you, next Tuesday, I believe, is the deadline for the extra credit project. If you're doing it, and if you're going to do it before the deadline, email me it, and I'll check it and tell you what's wrong so you can correct it. All right, let's get on with the review. And first of all, you should know what is a polymer. And a polymer is a macromolecule made up of repeating units called excuse me, monomers. Now, when we talk about polymers, there's two main ways of designating the type of polymer. One is by chemical property, the other is by physical property. And a physical property, there are two types, and that is the addition polymer and the condensation polymer. And you should know that a polymer with only one type of monomer is an addition polymer. Addition polymer has only one type of monomer. You should know examples of that are rubber car tires and saran wrap. There are others, but that's key ones. Now, for a condensation polymer, that's a polymer with two or more types of monomers. And think of condensing, bringing two things together. An example of a condensation polymer is this polyester, my water bottle. And if you had a nylon jacket, which I'm not wearing one now, that would be a condensation polymer. Now, the other type of way of classifying polymers is by a key physical property. And that is one type is a thermoplastic polymer. And you should know, once formed, a thermoplastic polymer can be reheated and reshaped. Again, thermoplastic polymer, once formed, it can be reheated and reshaped. And you should know examples of that are a water bottle, my plastic one, and saran wrap. By the way, there's no correlation between addition and condensation and thermoplastic. Now, the other type of physical property, key physical property, are for a polymer, thermoset polymer. Once formed, it cannot be reheated or reshaped. Again, thermoset, you should know, once formed, it cannot be reheated or reshaped. And you should know examples of that are rubber tires and urethane foam. If you're sitting on a nice seat cushion, that's urethane foam. If you look at your refrigerator, it's thin because the wall is the inside cold box and the outside is insulated with urethane rigid foam. Next, I talked about fats and oils. Now, lipid are molecules from plants and living things like you and me that are soluble in nonpolar solvents, but not in water. You should know a saponifiable lipid is a fat and oil, and a saponifiable lipid yields carboxylate anions of fatty acids of the reaction of that saponifiable lipid with base and water. Now, non-saponifiable lipid, also known as steroids, does not react with base and water. Now, what's a fat? You should know that's a solid or semi-solid triglyceride at room temperature. What's an oil? You should know that's a liquid triglyceride at room temperature. Again, fat, solid or semi-solid triglyceride at room temperature, oil, liquid triglyceride at room temperature. Now, the general structure you should know of any fat or oil is this. It's a triester. Ester number 1, ester number 2, ester number 3. As I mentioned in the videos, fats and oil chemists, otherwise known as oil chemists, and I'm a member, I don't do it anymore, AOCS, American Oil Chemist Society. The ones that make gasoline, those are called petroleum chemists. Those who deal with fats and oils are oil chemists. And we write our ester backwards. Where normal synthetic organic chemist writes the ester this way. This is the way it evolved. And here we have ester 1, 2, 3. All the reactions you learned for esters happens with fats and oils. If we take an ester and react with acid and water, you get back the alcohol and the carboxylic acid you would have used to make that ester. Well, here you have 3 esters. Each ester gives this alcohol together as glycerin, and you get these 3 carboxylic acids. If you react the fat or oil with base, sodium hydroxide and water, you get back the alcohol and the carboxylate anion you would have used to make that ester. And here you have your 3 esters. This ester gives this alcohol plus this carboxylate anion, and same for the other 2. And you get glycerin and these carboxylate anions. Now, one that I taught you, because I worked in the chemical and I worked in the fats and oils industry, is if you have steam reacting with an ester. And steam is hot water. And you can catalyze a reaction, make it go quicker, by chemical means, acid or base, or by, for a lot of reactions, running it at a higher temperature. And having hot water runs it at a higher temperature. And this gives you the same products as if you had done an acid hydrolysis of an ester. The alcohol and the carboxylic acid you would have used to make that ester. And therefore, you have this ester, actually triester, steam. The first one gives this alcohol plus this carboxylic acid. Second one, this alcohol, this carboxylic acid, and so on. So you get glycerin and these carboxylic acids. Now, the carboxylic acids from an fat or oil are called fatty acids. And I asked you to learn the structure of 2 fatty acids that I work with heavily. And one is stearic acid, 18 carbons, no double bond, otherwise called the saturated carboxylic acid. And oleic acid is a mono unsaturated, 1 double bond, and it has 18 carbons, and the double bond starts at carbon C9. 1 plus 7 is 8, and that makes this C9. And that can be cis or trans. And you have the rest of it, again, 18 total carbons. If I ask on a test, give the structure of stearic acid, you should be able to write it. If I ask on a test, give the structure of oleic acid, you should be able to write it. Now, when we come to fats and oils, you have a saturated fat, and that means it has only carbon-carbon single bonds. Now, if you write down only single bonds, I'll mark it wrong, because a saturated fat has a carbonyl, carbon-oxygen double bond. But saturated fat only has carbon-carbon single bonds. Unsaturated fat has at least 1 carbon-carbon double bond. And you should know these. Now, since I worked in this industry, I taught you, and you should know, tallow is beef fat, yellow grease is pig's fat, and white grease is another type, a higher quality pig's fat. Now, to give you a real feel about what's happening in the real world, I came up with this approximation right here for tallow, yellow grease, and white grease. And you have R sub S, which is a sterile group, R sub O, oleal, R sub S, sterile. The R sub O has a double bond in it. But for this part, we're using shorthand. And if I ask, give the product or products for tallow reacting with base and water, and there are 3 products, what do you do? Well, what I really mean is take this triglyceride, react it with base and water, and what do you get? Well, any ester, base and water, get back the alcohol and the carboxylate anion you would have used to make that. First one gives us alcohol plus sodium stearate, that's this. Second second ester gives us alcohol plus sodium oleate. And the third one gives us alcohol plus, once again, sodium stearate. So even though you get two of these for this reaction, the way I have it written, there are three different products. 1, 2, 3. And you should be able to do the same reaction of tallow, yellow grease, or white grease with acid and water. I've done base and water and with steam. Now, one of the most important things I will teach you all semester is how soap works. And you should know the structure of soap. Soap has a nonpolar tail, polar head. And you should know like dissolves like. And that's the key. If you go back and watch the videos, I wrote it in big letters because that's the most important thing, how soap works. And I should have added right here, water is polar, dirt and grease. Spelling error. Yeah, that's a bad looking E. Soap and dirt and grease are nonpolar. And like dissolves like, things that are similar polarity are soluble in similar polarity. And therefore, water won't get the dirt off your hands because dirt is nonpolar and water is polar. However, if you also use soap, which has a nonpolar tail, polar head, dirt attracts the nonpolar tail of soap and forms this micelle, and you should know that. And now when the micelle, and I've only put a couple of the dirt soap molecules and it's totally surrounded, it forms a micelle, and the outside of the micelle has the polar head. And now the micelle looks polar to water, and water says to the micelle, I'm polar, you're polar, let's go down to drain together. And they do. You should know this. You should know the structure of soap, the fact that like dissolves like is the key. What's the structure of a micelle and how does it work? Micelle looks polar to water and goes down to drain together. All right, I talked about steroids, your hormones. You should know how to draw the steroid ring system or skeleton. And it's a 6-membered ring fused to another 6-membered ring. Then up here is another 6-membered ring. And then right here is a 5-membered ring. And all your steroids look like that. Next, I talked about carbohydrates. And a carbohydrate is a polyhydroxyaldehyde, polyhydroxyketone, or a molecule that upon hydrolysis becomes a polyhydroxyaldehyde or polyhydroxyketone. When we talk about carbohydrates, this is a good time to talk about chirality. And you should know chirality means in Greek, handedness. And actually, a couple years ago, in one class at Chem 170, I actually had not one, but 2 students who were from Greece who spoke Greek and said that's what chiral means, handedness. Now, you should know what is an achiral object. And A means without chirality, handedness, and that's an object with a superimposable mirror image. I will never ask you what's the definition of achiral, but you should be able to identify achiral objects, like a sewing needle. And if you saw my videos, you saw how bad I draw. And a sewing needle is superimposable with its mirror image, and therefore it's an achiral object. You should also know chiral objects. A chiral object is an object that's non-superimposable with its mirror image, like your hands. My hands are mirror images, forget about the ring, and they're non-superimposable. Thumb there, none of the other fingers line up. Ring, middle finger, none of the thumbs don't line up, and a lot of other fingers. Now, as I said in the video, if you see in the name of a object right or left, immediately know it's chiral. If I say, is my right hand chiral or achiral? Well, it's right, it's chiral. If I say I have a left shoe, is that chiral or achiral? As soon as you see the word left, you know it's chiral. Next, I talked about chiral carbons. That's a carbon with 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. Oh, don't have it open. Now I have it open. And if I were to ask in this molecule right here, circle the chiral carbons. Well, the first thing I would do is eliminate carbons that are not chiral, achiral. And if it has 3 or more of the same atom, if it's in a double or triple bond, those carbons cannot be chiral carbons. Now, if I look here, there's 3 hydrogens, so this can't be. These are in a double bond. That can't be. This carbon is in a double bond. That can't be. And that leaves us with just 2 carbons to go. And this carbon right here has a hydrogen bromine, methyl group, and this whole thing I'll call R. And those are 4 different things. So I'd circle that. And if I look at this carbon, it has a hydroxyl group right here, hydrogen. This whole thing I'll call R, and a carbonyl and a hydrogen, an aldehyde, I'll call that R prime. 1, 2, 3, 4. And that would be the other one I circle. And you should know how to do that. Now, next I talked about enantiomers. Enantiomers are non-superimposable mirror images of a molecule. And about this time, I also talked about Fischer projections and about Emil Fischer, one of the great German organic chemists. And if I were to ask you, draw the enantiomer of that molecule, what do? Enantiomer means mirror image. Now, you don't have to do this, but I like to put my mirror in. The backbone will still be the same. This carbon is achiral, so I can write it this way. This carbon, because this, remember, CHOR is the same as writing the aldehyde this way, and sugar chemists do it this way. And therefore, this is an achiral carbon. But each of these carbons here, every intersection of line is a carbon, is chiral. So the first one, what's close to the mirror, the hydroxyl group, what's farthest away, hydrogen. Next one, what's close to the mirror, hydrogen, farthest away, hydroxyl group. Last one, close to the mirror, hydroxyl group, and hydrogen farthest away. And if you take your hand and put it up there, what you're holding closest to it, you'll see first, and the farthest away is the back of your hand. And that's how you do a mirror image. Marion, what would you like me to do another example of?
On the top of the page, you have that example there. Can you like re-explain it because I'm sort of confused?
I mean, this one right here doing the chiral carbons?
Mm-hmm. Yes.
All right, let's do another one. Through the miracle of a modern organic chemist, I can do another one for you. All right, do you see that on the screen? Right here. You see that molecule I just drew?
I see it.
Oh, good. All right, here's how you do it. If I ask you or any student, circle the chiral carbons, and A is this. How do you do it? Well, the quickest way is to eliminate the carbons that are not chiral. You have a chiral carbon has to have 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. If it's in a double bond or triple bond, or if it has 2 or more hydrogens, it can't be chiral. So immediately I can say this has 3 hydrogens, it's out. This has 2 hydrogens, 2 or more, this is out. Well, this I don't know about. This has 2 hydrogens, it's out. This has 3 hydrogens, it's out. If it has 2 or more hydrogens, it can't be chiral. If it's in a double bond, either with another carbon or oxygen carbon, it's out. So we've now eliminated all those. The only thing that's left are these 2 carbons. Let's look at the first one. By the way, this is a sulfur. This has a thiol group, sulfur, hydrogen. This, I'll call those 2 carbons R. And these 4 carbons plus a chlorine and oxygen, I'll call R prime. And are there 4 different things on that carbon? Yes. Hydrogen, thiol, R, and R prime. So I'll circle it. And now look at the other carbon we have left, this one. It's got a chlorine, hydrogen. These 2 carbons with the carbonyl, I'll call R. And this side attached to that carbon, all of this, 4 carbons with a thiol group I'll call R prime. And are there 4 different things? Let's find out. 1, 2, 3, 4. So there are 4 different groups or things, and that's chiral. Does that help?
Yes, that helps. Thank you.
You're welcome. Now, when it comes to sugars, there are 2 I talked about, glucose and fructose. You don't have to know the structures, but it helps to be familiar with it. And there are 2 reactions that are equilibrium I asked you to learn. From test number 2, you learned that if you have an aldehyde or ketone, alcohol, acid, you get a hemiacetal or hemiketal. When both are in the functional groups, are in the same molecule, you don't need the acid catalyst. And here on C5, this alcohol attacks this carbonyl and forms this hemiacetal. You should know this reaction. Again, the same reaction, aldehyde or ketone, alcohol, acid catalyst gives a hemiacetal or hemiketal. You should know this reaction for glucose. Again, on C5, this carbon, the hydroxyl group attacks the carbonyl. This carbon and forms this. And you should know how to do that. If I ask you, give the starting material for this reaction, I don't give you fructose, you should know how to go backward. Same thing with glucose. And that was in the problem set. Now, I taught you how you can take a hemiacetal and react it with a different alcohol to get an unsymmetrical acetal or ketal. And where this plays an important role is with glucose reacting with another alcohol. And here's the general reaction you should know how to do, because this is the basis how glucose comes together to form starches. And you should know sucrose, table sugar, are fructose and glucose bond together. Starch is poly. Remember, poly means many glucose molecules together. And because of that, if I take a lot of glucose molecules and react it with acid, you'll do this reaction here and link them together to form starch. Now, the linkage between starch is an acetal linkage, and also in sucrose. And if you take sucrose and acid and water in your stomach, it breaks it down to fructose and glucose. If you take starch and acid and water, remember your stomach, and one of the miracles of life is we all have cells that make hydrochloric acid, H+, and you have water in your stomach. That's how you break down starch. You take that and react it with acid and water, and you get glucose. Now, leaving my class, and especially for test number 4, you should know how to describe with words and a general reaction what happens when you eat a fat or oil. And what's the functional group in a fat or oil? An ester. And in your stomach, you have water and acid, so it's acid hydrolysis of an ester. And the general reaction you learned for test number 3, ester, acid, and water, you get back the carboxylic acid plus the alcohol you would have used to make that ester. Again, you should know how to describe with words and a general reaction, what happens when you eat a fat or oil? And with words, that's acid hydrolysis of an ester. And there's the general reaction. Ester, acid, water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. You should also know at this point how to describe with words and a general reaction what happens when you eat a carbohydrate and what functional group holds carbohydrates together. An acetal. And how do you describe how you digest, eat a carbohydrate? As acid hydrolysis of an acetal. And the general reaction that you learned for test number 2 was acetal or hemiacetal, acid and water. You get back the aldehyde or ketone plus the alcohol you would have used to make that. Again, what is the functional group that holds glucose together and carbohydrates? And that is an acetal. And you should know how to describe with words and a general reaction what happens when you eat a carbohydrate. In your stomach, you have acid and water, and therefore it's acid hydrolysis of an acetal. And here's the general reaction: acetal or ketal, acid and water, get back to ketone or aldehyde, and the alcohol you would have used to make that acetal or ketal. And with that, I'm done for this review. I'll be posting it. Next week is our last week together. Boy, this summer semester zoomed by fast. I hope you've enjoyed it. And let me know, and better yet, if you like what I did this summer. I know we didn't see each other live face to face, but you saw the videos of me, which would be the same as if we were face to face. Go to ratemyprofessor.com and put something nice about me there. Now, if you didn't like what I did this summer, go to ratemyprofessor.com and put something not nice about me. Hopefully you like what I did. And with that, I'm done for the evening. Have a great rest of the day. Don't forget to study for Monday for test number 4, and also start studying after test number 4. You'll have a couple days to study for the final. And with that, I'll say, gang gesund. Goodbye.